Good afternoon, ladies and gentlemen, and welcome back to the live demonstration area. For the next 2 days, we are going to be witnessing state-of-the-art demonstrations. This is the place to be to see all the latest technology that is shaping the landscape for component parts manufacturing processes. This live demonstration is something new happening at the JEC, and we are very pleased to thank our partners, Thermwood, Aerovac, Composite One, MVP, and Rock Tools for making this experience possible. Ladies and gentlemen, the demonstration will be happening in English, but if you would like to have a live simultaneous translation in French, don't hesitate to get headphones from the hostesses. Mesdames et messieurs, c'est une présentation en anglais. Si vous souhaitez une traduction simultanée en français, n'hésitez pas de prendre un casque des hôtesses. And now let's dive into this afternoon's demonstration with Thermwood. Thermwood has been the market and technology leader in large format additive manufacturing since 2016, thanks to their innovative LSAM large-scale additive manufacturing systems. To present Thermwood's game-changing technology, we are very pleased to welcome Scott VAAL, who is the LSAM product manager, and Dr. Eduardo, BAROCIO, the Assistant Director of Additive Manufacturing from Purdue University. Thank you, Scott and Eduardo. The demonstration floor is yours.
Thank you. Well, hello everyone, and welcome to Thermwood's LSAM booth. I am Scott VAAL, the LSAM product manager for Thermwood. I am pleased to have the LSAM 510 additive printer printing live for you here today, and it happens to be one of the smallest models that we offer. In case it's not already obvious, LSAM is Thermwood's large-scale additive manufacturing system for thermoplastic polymers. It comes in a broad range of sizes, up to 15 foot by 40 foot by 5 foot, or 4.6 meters by 12.2 meters by 1.5 meters. And this length can actually increase on our flagship models up to 100 feet, or 30 meters. LSAMs are available in print-only versions and versions that have a print head and a 5-axis CNC router head on the same machine. In fact, some of our machines can actually print and run the router at the exact same time. So of course today we want to talk about large-scale 3D printing, but more specifically about large-scale 3D printing with high-temperature materials suitable for autoclave tooling applications. In fact, that's what we're printing live for you here today. With help from the research team at the LSAM laboratory at Purdue University, a full circle demonstration and detailed study was performed on a Thermwood autoclave tool for a composite air inlet duct. This mock-up tool was created with inspiration drawn from the NASA X-59 experimental supersonic aircraft. This study proves that composite tooling can be successfully created and used in high-temperature autoclave applications. In fact, the tools and the parts done in this study are with us here today. And as we speak, another set of tools are being printed. We want to explain the important steps needed to being successful with this process. From how we achieve quality LSAM prints to successfully compensating for anisotropic CTE and other shape changes that happens during the autoclave cycle. And it's also important to understand and compensate for pre-preg material spring, which happens on the laminate layup material itself during its cure process. I would also like to mention that this study shows that LSAM printed tools have excellent shape stability after multiple autoclave cycles, showing that longevity can be expected. So with all these factors considered and understood, we can create first-time right autoclave tools that have vacuum integrity directly off the machine and produce dimensionally correct finished parts. So what's required to do this? The key to successfully creating autoclave tooling starts with Thermwood's LSAM, which delivers superior print consistency. It has dynamic control of print temperatures and has the large-scale focused slicing software needed to create quality print programs. And then we finish this off with the confidence delivered through predictive simulations via the Composites Manufacturing and Simulation Center at Purdue University. So let's explore how the LSAM produces superior print consistency. First, the LSAM is the only machine equipped with Thermwood's patented melt core system for processing materials. The melt core is designed for high output deposition rates to produce large, consistent bead sizes. With our standard melt core, it can produce 200 pounds an hour, or 90.7 kilograms per hour. And with our optional larger melt core, we can produce over 500 pounds per hour, or 227 kilograms per hour. We use a PID heater control to tightly maintain processing temperatures up to 450 C. The heart of this melt core system combines a custom industrial quality extruder, a polymer melt pump system, and a temperature-controlled compression following wheel. This combination produces the most accurate and consistent beads possible, resulting in superior bond between print layers and the best solidity between neighboring beads. So let's break down these three components. First, the melt core's extruder screw and melt pump system work in complete unison to provide the most accurate and precise material output possible. In large-scale 3D printing, the extruder screw must change speeds constantly, or RPMs. So this custom patented screw design provides a more consistent melt temperature across these ever-changing speeds. Also, it is known that an extruder alone will not produce a consistent material output due to extruder surging. This is especially a problem at high output rates. So our extruder's only job is to keep a positive displacement melt pump system fed, and then the servo-controlled melt pump precisely delivers material to the nozzle. This eliminates the problem of extruder surging and produces the most accurate and consistent material output possible. And an added note, it is not necessary to change our extruder screw just to change to a different material. And last but certainly not least, the compression following wheel. An important factor to understand is that unlike other systems, our melt core delivers material to the nozzle, but the patented compression following wheel finishes the bead's final shape and dimension. This provides active bead compaction, which is important. The nozzle tip is actually slightly above the finished bead's height, so it doesn't have to drag through the material to produce the final bead shape. This prevents excessive material from building up on the nozzle that can be harmful and detrimental to the surface quality of your print. The compression following wheel is temperature controlled, but only to prevent polymer affinity, which is the material wanting to stick to the wheel. It's actually quite hot during the printing process. In fact, a study performed by a group at the LSAM Research Laboratory further emphasizes the benefits of active bead compaction. Bead compaction aids in the removal of interbead voids. It improves consistency in the printed composite microstructure, which includes repeatable fiber orientation. It enhances interlayer bonding, and it provides the best results for lateral bead-to-bead solidity. Excuse me. You cannot achieve quality prints if you can't hold your parts secure through the entire printing process. And in the large-scale world, it can be a little more tricky and maybe a little bit more important to hold these parts. The LSAM solves this issue with its patented beadboard print substrate. It provides a strong initial tack, and it allows the printed part to float during the initial contact. Then, after those initial layers cool, it'll hold strong through the entire print process. This prevents the distortion and stresses that build in other substrates. Excuse me. Been talking a lot. And in fact, the beadboard holds strong enough that initial machining operations can actually be done while still attached to the board. And of course, when ready, they can be easily removed with just a few simple everyday tools. They are reusable and repairable. Let me also mention that LSAM has a wide variety of print-ready materials that are ready to use. Using any of these materials requires a simple one-click activation to apply all the settings necessary to print that material. And because of our fixed displacement metering, material configuration files can be confidently shared amongst all LSAM machines. It also has automatic routines to load, empty, and purge material and clean material from the system, with on-screen instructions to guide the user through all the steps. Now let's explore how the LSAM controls print temperatures. Achieving and maintaining optimal print temperature during the printing process is extremely important. If you print too hot or too cold, you can experience varying problems from weak bonds to excessive part deformation. We must allow enough time for the printed polymer to cool to the ideal temperature range before printing that next layer. So, layer time control, a patented technology built into the control system of the LSAM, automatically controls the time spent, automatically controls the time spent on the layer by adjusting the print speed. This is dynamically handled at the control system and keeps the temperature within the proper temperature range. And should conditions change, excuse me. And should conditions change, layer time can be immediately adjusted, all while the machine is printing. Maintaining this temperature range results in superior and more consistent fusion between layers. Next, let's explore LSAM's large-scale focus slicing software. Excuse me. Producing superior prints requires slicing software that's suitable for large-scale additive. So Thermwood developed LSAM Print 3D, which understands all the printing characteristics of the LSAM. It has all the typical features of traditional slicing softwares, plus loaded with unique custom features needed for large-scale additive. A notable plus is that it creates print programs directly from real CAD data formats, such as solids, surfaces, and sheet bodies. So there's no need to create a deteriorated quality STL just to create a print program. LSAM Print 3D has been used in well over 100 technical demonstrations for LSAM customers, not to mention our own printing and testing. There have been countless print programs created by LSAM owners as well. This experience has driven the features in LSAM Print 3D and has been continually refined for over 8 years now. This has resulted in unique, invaluable, patented features targeted for the LSAM and large-scale additive. So at this time, I would like to pass the baton to Dr. Eduardo BAROCIO to talk about predictive simulations.
All right. Thank you so much, Scott. Well, it's a pleasure to be here today and talk a little bit about the technology we bring to, simulation technology we bring to this large-scale additive process from Thermwood. So our overarching goal at the LSAM Research Laboratory is to augment the confidence on this technology by enabling first-time dry printing and first-time tool production through physics-based simulations that have been developed on a solid scientific foundation. So we have a lot of expertise in modeling manufacturing process. We have a particular virtual twin for the LSAM process called Additive 3D. We also have extensive composite characterization capabilities and experience. And today I would like to walk you briefly through this end-to-end virtual twin for additive manufacturing called Additive 3D. So we basically replicate the process of depositing material bit by bit by activating elements in a finite element model and solving multiple physics simultaneously, okay? So you can see in this diagram, we take the machine code that is used to drive the physical system to drive a physics-based simulation of a print process, where we can predict, let's say, temperature history, the crystallization of polymer, if we are printing with a semi-crystalline polymer, the residual stresses, deformation that might occur, not only during the print process, but also after the part is removed from the substrate. But really important, we can then investigate the performance of the as-manufactured shape. In other words, considering all the effects of manufacturing, such as the anisotropy of the printed material, the local orientation of the printed bit within a printed geometry. Just to dive a little bit into what is under the hood of Additive 3D, so there are two key inputs. One is a machine card, and the other one is a material card. So the machine card clearly contains all the aspects of the process and the machine that are important for the outcome of the print process. Those include interactions of the part with the substrate, interactions of the part with the ambient inside the machine, the effects of flow in the orientation of fibers within the printed bit, because at the end of the day, the fiber orientation controls all the mechanical, CTEs, thermal, and viscoelastic behavior. Then the material card is informed by the machine card because we need to have that fiber orientation information. So the material card contains a wide range of material properties that we need to describe the different phenomena that occur as the material is laid down at the melt temperature and then cools down to the ambient temperature. So those two material machine cards inform the physics-based pro simulation. It's a transient simulation. We basically carry out a sequentially coupled thermomechanical analysis that allows us to basically predict temperature, crystallinity, interlayer bonding, residual stresses, deformation, and be able to iterate virtually and avoid expensive print trials that might result in a print failure. But then we can take the information of the as-manufactured shape and investigate its performance characteristics. Performance clearly depends on the context where the printed part is going to be used. If it's a mold, like in this example, there is an isotropic shape change that occurs as the mold goes in the autoclave. So we can predict and compensate for that, so that we machine a compensated shape that is going to develop the right shape when it goes in the autoclave. Now, elaborating a little more on this example that we're demonstrating today. So we did a basically full circle of simulation-driven design, where we first started with the desired composite part geometry, which was inspired on the X-59 aircraft. Then we predicted the shape change of the composite laminate, you know, the spring back that everyone here is familiar with. Then we designed a tool for the LSAM process. We predicted and compensated for the shape change of the tool, and then we do a fully integrated simulation where we consider the part manufactured on the printed tool and verify that we in fact got or produced the desired composite part geometry. Now, just to give you a brief demonstration on the additive process simulation. So as inputs, we need the machine code that is used for the physical process. We need a machine card, and we need a material card. And then we can predict, you know, residual stresses, temperature, deformation. So in this particular example, you can see here on the left-hand side, the evolution of temperature throughout the print process. Clearly, the simulations are just accelerated by a factor of 10, just to visualize it quickly. But you can notice the large temperature gradients that develop not only along the height of the part, but also across the thickness of a printed section. Simultaneously, we see on the middle, the stresses developing in the stacking direction, and then on the right-hand side, basically deformation occurring in the y direction. As you might notice here, the tool itself is actually springing in as it's being printed. So we predict that, accounted for that, and created a compensated shape that after printing comes to a shape that we can machine. You can see there the arrows pointing in the direction where the spring-in occurred. Now, we also did a systematic study of the shape stability of this tool after multiple cycles. So we actually, you can see in the first image on the upper left corner, we did a layup for a prepreg system that is cured at 180 Celsius in an autoclave. So we did multiple cycles in the autoclave, and then after each autoclave cycle, we laser scanned the surface to perform a deviation analysis. So you can see there in the bottom left corner a plot of the deviation between the shape at the beginning of the study and the shape after multiple cycles. So in general, the shape change is of less than 100 microns, basically, throughout multiple shapes. So this proves that shape is really consistent throughout. So now we deliver these technologies through an industrial consortium at Purdue, where we basically provide access to Additive 3D to enable first-time dry printing. We provide access to the Thermwood LSAM system that we have in our facility to demonstrate the technology and enhance the confidence in this technology. So we walk members step by step on how we use simulation to drive the design for additive and also to compensate for, let's say, shape change in autoclave tools, etc. We provide quarterly webinars. These webinars really focus on addressing problems, practical problems posed by members of the consortium. And we provide practical solutions for those problems grounded on a strong scientific foundation. So we do a lot of fundamental research, but really geared towards solving problems of relevance to this industry. And then the last but not least important, we provide technical support around all this concept of the large-scale additive process. Now, I would like to just wrap up and reinforce basically those key elements that we convey in this presentation so that I make the LSAM system unique. So there is my colleague Scott walk us through some of the details of why the LSAM provides superior print consistency. It has a uniquely and patented technology for the melt core and the compression wheel. There is also some unique features for dynamic print speed control to a layer time control that is built in the controller. And there is also a unique slicer that gives you a lot of flexibility that is not often found in typical slicers. And last but not least important, all the simulation technology that we bring to this technology area to enhance the confidence on this technology. And with that, we'll be happy to take any questions that you might have. Here.
Any questions from the audience?
Any questions?
Okay, I have a question for you, gentlemen.
Yeah.
Eduardo, what kind of experimental validation has been done for Additive's 3D?
Yeah, so we've done an extensive experimental validation of the simulation predictions. So at different stages of the simulation predictions, so for example, every time we develop a new material card or a new machine card, there is a series of blind predictions that we do and then compare against experimental measurements. Experimental measurements of deformation, temperature history, crystallinity throughout the print process. And our ultimate goal is to basically provide a predictive simulation. So if something doesn't match quite well with the experimental measurements, we go back and revisit the fidelity in the different material models and basically augment the fidelity so that we truly develop a predictive tool.
Okay, thank you very much. Scott, can you tell me what is the typical print bead size on an LSAM?
Yeah, the typical bead size is 0.83 by 0.2 or 21 millimeters by 5 millimeters. This is an optimal bead size. We can print pretty much any bead size, but that's an optimal size that works very well for maintaining the heat that's necessary to get the great bonds that we get with our printer.
Okay, thank you. Eduardo, I have another question for you. What physics are captured in Additive 3D?
Yeah, so there's a wide range of physics, basically starting with anisotropic heat transfer. So there is temperature-dependent thermoconductivity that depends also on how the fibers are oriented within the printed material. So we use an isotropic heat transfer model there. There is also, we model the heat losses due to the compactor. If we use a compactor, there is heat removed from the compactor. Then there is also differences in convection that occur within a printed part depending on whether it's an exposed surface or it's an internal surface. So those have different convection conditions. There is also an isotropic shrinkage that occurs not only due to the coefficient of thermal expansion, but also the crystallization in the case of semi-crystalline polymers. There is an isotropic viscoelasticity. So even though we use carbon fiber reinforced polymers, fibers are short and discontinuous, and it's surrounded by a polymer. So we still have some of the relaxation phenomena from the polymer. So that's why we use a viscoelastic model there. We also use or capture interlayer bonding, which is driven by diffusion, so that we can predict at every point in the print the fracture toughness in between the layers. And last but not least important, there is a series of different modeling techniques to capture the interaction of a printed part with the substrate. So.
Okay. Fantastic. So thank you so much, Scott and Eduardo. Ladies and gentlemen, if you would like to ask them further questions, take advantage. They are here, the experts on LSAM technology. Otherwise, you can also visit them at their stand, which is just behind in Hall 6 at P52. And they will be back again tomorrow at 2 o'clock for another demonstration. Thank you very much, gentlemen.
Thanks, everybody.
Thank you, everyone.
Ladies and gentlemen, the live demonstration area continues in another 15 minutes. We will have Aero back here, so don't hesitate to come back. Otherwise, enjoy your afternoon at the show. Thank you.